Okay, so I wanted to go back to the sealed bids method. All right. This was the last type of fair division thing we were going over, just to remind you, get you back into the mindset of fair division. So on our methods of fair division, we have divider chooser method that guarantees fair division. We have a bunch of different divider chooser methods, I should say, of fair division. We have lone divisor, lone chooser, last diminisher. All of those are basically divider chooser methods. And then we had the sealed bids method that we saw here, where you bid a monetary amount. We had the adjusted winning procedure where each person gets 100 points and then you spend it and adjust it. Here, we involve a monetary amount. We did a couple of examples of that. So, between all of our divider chooser methods, between the adjusted winning procedure and the sealed bids methods, we saw a lot of how to divide up a bunch of goods. What we're going to do now is we're going to shift our focus a little bit to how do we divide up representatives. Okay. And that's the concept of apportionment. How do we divide up representatives? And the easiest reference that we have in the United States is probably the House of Representatives. So the House of Representatives has a fixed number of representatives, and we need to divide those up between the various states. Because some states are more populous than others, they're going to get more representatives. And because some states are less populous than others, they're going to get less representatives. So California has more representatives right now, I believe, than any other state, because it's the most populous state. Michigan has more representatives than South Dakota because Michigan is more populous. And you may think, well, this is going to be nice, but in the general concept of apportionment, how we split up representatives, we need to do so in a fair way. We need to make sure that each district or each state or each whatever gets their fair share of representatives based on the population. Sometimes we may think, well, that sounds fairly straightforward. We'll just give them their fair share. And it's just a mathematical process, right? But it's not quite that easy because the population of states are not equally divisible. Just because Michigan has 9 representatives, or however many we have, doesn't mean that our population is exactly 9 times Wyoming, which has 1 representative. Okay. So here is one of the first attempts at giving or allocating representatives. It's called Hamilton's method, named for Alexander Hamilton. Okay. So what Hamilton's method does is it says, we're gonna look at the population of every district. We'll say district or states or whatever. And we're gonna get a quota of representatives for that state using what's called a standard divisor. I'll get to calculating a standard divisor here in a moment. So what they do is they take each state's population and they divide it by a certain number. That number is called the standard divisor. Most of the time, we get a decimal version. So let's say we got, 15.28 as after we divided by the standard divisor. We're going to round that number down and say, well, that's 15. And we're going to give every district or every state their lower quota. That lower quota is the one where I lop off the decimal version. Because I have given every state the lower quota, we're going to have some additional representatives that we need to allocate. And the way we do that is we give it to the highest remaining decimals. This will make a little bit more sense when we get into the details. So let's talk about what a standard divisor is. The standard divisor that we're going to use is a ratio of the total population to the number of representatives that we want. If you think about that, that basically means how many people per representative, how many people should be represented by each representative in an ideal world. That makes sense? So that's the standard divisor. Total population divided by the total number of representatives. And what we're going to do is we're going to calculate every district's, again, think district, state, municipality. I'll keep using the word district here because that's what a lot of the books do. So that's what I'll use for. So a quota for each district is the ratio of the district's population divided by that standard divisor, or technically any divisor. Okay. So we take the district's population over the standard divisor. That's what we mean by quota. So standard divisor basically gives you how many people should be represented by each representative. And a quota is going to say, well, how many representatives in an ideal world would this district get? And the trouble with a quota is, once again, a lot of times these quotas are going to come back with decimals. And we cannot allocate 0.28 of a representative. Does that make sense? All right. So again, Hamilton's method, we use the standard divisor, we get those quotas. We give every district their lower quota, and then the extra representatives that we haven't given out yet are given to the highest remaining decimals. All right. Let's do an example. Let's pretend there is some place out there where we want to allocate 100 representatives to these 5 districts. We'll call them districts A, B, C, D, and E. Now, the total population is the first thing I need to calculate. I have to add up the population of all 5 districts. The total population there when you add up all 5 districts is 100,000. All right. So total population is 100,000, and we want 100 representatives. So let's take the let's calculate the standard divisor. Standard divisor is going to be 100,000 divided by 100. Which gives me 1,000. And roughly what that means is that in an ideal world, each group of 1,000 people would have their own representative. Can I follow that? So each group of 1,000 people would have their own representative. Now, just as an example, I'll write this on the table in just a moment. But if you look at district A, District A had a population, I believe, of 38,343 individuals. Let me double check that real quick. Yeah, 38,343. Okay. So District A's quota is going to be that number divided by 1,000. Now it's pretty easy to divide by 1,000. You just move the decimal place over 3 spots, right? So you get the number 38.343. The lower quota there is 38. You just lop off the decimal. By the way, even if the decimal was like 0.972, you'd still just lop off the decimal. Does that make sense? That's what it means to do the lower quota. Lop off the decimal. So this is how we're going to calculate the quota and the lower quota, and we'll do that for all 5 districts. I wanted to do it, at least write it out once this way, so you see what's going on, because when you put it into a table format, like we're going to go from this step to this step to this step. might not be as easy to follow. Does that work? And you might say, well, why do you keep them in the decimal places over 3 spots? That's because dividing by 1,000 does that. And this standard divisor is really nice to deal with. I made it that way on purpose, but a lot of times these standard divisors will be uglier numbers. You know, if they're 837 if 837 was your standard divisor, it's a harder dividing job. Okay. So let's take a look and start filling out this table. And I'm going to copy and paste just like I keep doing. Like I've done a bunch of times before. All right. Move that way. Go. And I'll adjust the zoom as well. Okay. We got it. So we know the standard divisor is 1,000. So we're going to keep using that. So population divided by 1,000 gives me the quota. In this case, 38.343. When I take 21 to 30 and divide it by 1,000, I get 21.230. When I take 4,899, divide that by 1,000, I get 4.899. 20,405. Divide that by 1,000, we get 20.405. Divide 15,123 divided by 1,000, you get 15.123. Again, I made it really easy to divide on purpose in this example. So we get 38, 21, 4, 20, and 15 as the lower quotas. Everybody see that? I just lop off the decimal parts. So lop off the decimal parts and you get that. Now, what we're going to start doing is we're going to say we're going to guarantee A, therefore, has 38 representatives. We're going to guarantee B has 21 representatives. We're going to guarantee C has 4 representatives. We're going to guarantee D has 20 representatives. And we're going to guarantee E has 15 representatives. If I add those all up, we have 98 total as the lower quotas. Does that make sense? So we need to add should have wrote it this way. So we need to add 2 more representatives. Everybody okay with that? So what we go back up and do is we say, what were the highest decimals that we locked off? So I ignore the whole number part and I just look at the decimal version. Here we have 0.899. There's nothing bigger than 0.899 out there. So that is the highest decimal that I lopped off. So I'm gonna add one representative to District C. What's the next highest decimal that we've lopped off? Well, here's 0.343. Here's 0.230. We already had one there. 0.405 and 0.123. The next highest decimal is the 405, isn't it? So we're going to also add 1 to 20. Now that we've added 2 representatives, Hamilton's method is essentially done. We're going to give A 38 representatives. We're going to give B 21 representatives. We're going to give C 5 representatives. We're going to give D 21 representatives. And we're going to give E 15 representatives. See what I did there? On the allocations. On the allocations, I just added 2 more. And they went to the highest decimal that I lopped off. And so that's what Hamilton's method does. That's the essence of Hamilton's method. I calculate the standard divisor. I divide every district's population by the standard divisor. Give everyone the lower quota, and then ask how many more representatives do we need to add? And then we add those representatives to the biggest that we lopped off. Is that right? Here's another one. This one's going to be very similar with 100 representatives. I want you to try this one on your own. I think this one also has 100,000. I think I made it that way, but. Yeah, also has a population of 100,000. All right, let's see how this one's gonna work. Again, I'm just gonna copy and paste this table, so hang with me for a second. Might as well start on a new page. All right. All right. So, like I said, the total population is 100,000 once again. It's not always going to be 100,000, okay? But that forces my standard divisor since I want 100 representatives to be equal to the fraction 100,000 divided by 100, which is 1,000, right? So my standard divisor is going to be 1,000. So the quota for each of these, once again, it's an easy divide. 48.343, 5.610, 4.350, 30.349, 11.348. Lower quota, lop off the decimals. 48, 5, 4, 30, 11. This time, if you add up those lower quotas, 48 plus 5 plus 4 plus 30 plus 11, you get 98. By the way, you're not always going to get 98. Sometimes you'll get 99. Sometimes you could get 97. You know, you could be 3 off, you could be 2 off, you could be 4 off. Doesn't matter. But we have 98 as our total lower quota right now. Okay, follow that? So we need to add 2 more. So I go to look at the highest decimal that's left. The first highest decimal is 0.610. So I'm going to add that. The next highest decimal, is it 0.350? I think that's right. 0.350. There's a lot of 0.3s though. So with Hamilton's, the number of representatives for each district, in this case, where we wanted 100 representatives, is as follows. 48 for District A, 6 for District B, 5 for District C, 30 for District D, and 11 for District D. Okay. And that gives us 100 representatives. Everybody get that? How this process works? So it's not an easy formula, but it's something that you can do in a straightforward process manner. Now, we're gonna all do example 3 together. We're gonna take that same table, and instead of saying we want 100 representatives, let's say we want to add a representative. Let's say we want to have 101 representatives. Okay. So let me show you how that is going to change things. Once again, I have to adjust this. I'm going to say reps. All right. Sorry. All right, that's better. Okay. So the representatives that we want now are 101 representatives. We still have a total population of 100,000. So our standard divisor this time is going to be equal to 100,000 divided by 101. If I take 100,000 and divide it by 101, I get 990.099. I'm just going to take and round that to 990.10. Is that okay? I'll round it to 2 decimal places, in other words. So our standard divisor rounded to 2 decimal places. Let me rewrite that. It's 990.10 or 990.1. So in order to get each quota, I'm going to take each population, and now I'm going to be dividing it by 990.10. So I'm going to take my 48,343, divide it by 990.10. That gives me 48.82638. I'm just going to round that. I'm going to go out to 3 decimal places, but you can go out to 2 if you wanted to. I think 2 will work. I'm nervous we're going to have to decide something on rounding to 3, but 5610 divided by 990.10 is 5.666. 4350 divided by 990.10 is 4.393. 30,349 divided by 990.10 is 30.652. And then 11,348 divided by 990.10 is 11.461. We're okay with that? So each quota came from the district's population divided by 990.10. So the lower quotas are 48, 5, 4, 30, and 11. Once again. That's again, now that we've added those up, the lower quotas accounts for 98 representatives. So we need to add 3. To reach 101. Everybody okay with that? Remember, we wanted 101 representatives. We have 98, so we need to add 3 of them. So we take the biggest decimals. The first biggest decimal is this one, the 0.826. So we're going to add 1 representative to District A. The next biggest decimals are B at 0.666, so we're going to add 1 to that. And the next biggest decimal is 0.652, so we're going to add 1 to D as well. That means in Hamilton's method, with 101 representatives, District A gets 49, District B gets 6, District C gets 4, District D gets 31, District E gets 11. Oh. Okay. Does that make sense? So 2 things about this. You don't always have to have really nice numbers of representatives or nice populations or really nice standard divisors to work this out, okay? If you do come across where your standard divisor is some ugly number, just round it to 2 decimal places like we did here, okay? So you can have ugly, you can, allocate 335 representatives if you wanted to, and see what you get. Here's another detail that's really weird. I want you to notice that when we had 100 representatives, notice that District C got 5 representatives when we had 100. Okay, follow that? However, when we added 1 to the system, District C actually lost a representative, and 2 other districts, namely A and D, actually both gained 1. Can you follow that? So District C lost a representative, even though the total system gained a representative. This has to do with how we got the decimals. The decimals were just by division. So District C lost a representative while 2 others gained 1. That's a really weird concept. It doesn't seem like it should be right. It seems like if you add representatives to the system, those representatives should just go to, maybe other districts. But one state or one district shouldn't lose 1. This is what's known as the Alabama paradox. And it's basically what I'm just describing. C lost a representative, while in total, the whole system gained a representative. So the whole system gained a representative, and then C lost theirs. And the one that was gained and the one that was lost got distributed to 2 different districts, apart from C. So this is called the Alabama paradox. And it can happen in Hamilton's method. Okay. Now there are other paradoxes as well that can happen here. I'll try to go through this fairly quickly. All right. Let's take this example. I'm going to calculate what's the total population. I got a total population of 10,000. Okay, well that's nice. It's a nice number to deal with. 10,000 is the population. I already said that. I didn't see that earlier. And let's say we want 100 representatives. This one I didn't write a lower quota column, but you can imagine what that is. So if we have, or we want 100 representatives, and our total population is 10,000. The standard divisor is going to be equal to 10,000 divided by 100. And when you do that, you get 100. So every 100 people, ideally, would have their own representative. So to calculate the quota, we'll divide each population by 100. So 2595, when I divide that by 100, I get 25.95. When I divide 702 by 100, I get 7.02. When I divide 1,992 by 100, I get 19.92. Then I get 38.70. Then I get 5.73. And then 2.68. Is that right? Now, if you look at the lower quota, I basically just pretend the decimals don't exist. And I say 25 plus 7 plus 19 plus 38 plus 5 plus 2. That would give me 96. In total. Which means I need to add 4. So I'm going to look for the 4 highest decimals. Is that right? 0.95. That's one of the higher ones. 0.92, that's one of the higher ones. 0.73, that's a higher one. 0.70, that's the higher one. Okay. Notice what I'm getting here. I'm getting that District A is going to have 26 representatives. District B is going to have 7. District C should have 20. District D should have 39. District E should have 6. And District F should have 2. Is that right? So let's say something happens. Let's say that there's a change in my populations. Certain districts gain people at faster rates than others. Right? So let's pretend that happens. And the total system gains 78 people. All right. So it's kind of like every 10 years in the United States, we do a census. And then based on that census, they reallocate which states get how many representatives in the House of Representatives. Let's say that happened. In fact, let me just oops. I guess I could have. I'm going to do it this way. Okay. So once again, we want 100 representatives, but now my population changed to 10,078. And so my standard divisor is going to be what we get when we take 10,078 and divide it by 100. I get 100.78. Right with that. So to get each quota, I'm going to take each number and divide by 100.78. So in District A, 2635 divided by 100.78 gives me 26.146. 712 divided by 100.78 says that the quota for District B should be 7.065. 2011 divided by 100.78 gives me 19.954. District D, 3872 divided by 100.78. 38.420. 580 divided by 100.78 gives me 5.755. And 268 divided by 100.78 gives me 2.659. So if you look at the lower quotas here, just lop off the decimals. We got 26, 7, 19, 38, 5, and 2. The lower quotas, therefore, add up to 97. So we need to add 3 more. Those 3 are going to go to the biggest decimals. Biggest decimal is 0.954. That's in C. Next biggest decimal is 0.755. That's in E. And the next biggest decimal is 0.659. That's in F. So with the population adding, A got 26 representatives, B got 7, C would get 20, D would get 38, E would have gotten 6, and F would have gotten 3. Is that right? Is putting a little plus sign there enough to see what's going on? That's how I like to do it. Just so I know which ones I'm adding to and which ones I'm not. Now I want you to compare this to our previous example. So we got 26, 7, 20, 38, 6, 3. 26, 7, 20, 39, 6, 2. Notice that District D and District F swapped a person, a representative, right? District D's representatives went down by 1, and District F representative went up by 1. Okay. And you might think, well, that would make sense if District F gained in population and District D lost in population. But here's the really weird thing. Look at the population of District D and then the population of District F. So District D, had 3870. District F had 268 before the population change. After the population change, F didn't gain any population. But D actually did. D gained 2 people and lost a representative, while F gained 0 people and gained a representative. That's really, really odd, right? That one district could lose representation while gaining in population, and another district could gain representation while losing in population or staying the same. In this case, staying the same. That's kind of a paradox and a weird thing that can happen. And this paradox is called the population paradox. It's exactly what we said. District D gains 2 people, but loses a representative. District F gains no people and gained a representative. So these allude to a couple of the weird intricacies and what some people would call troubles with Hamilton's method. One of those is what we described earlier, which is the Alabama paradox. You increase the total number of representatives, the population stays the same, but one district loses a representative while the whole system gained 1. The population paradox is where we increase the total population. A growing district loses a representative while a stagnant district actually gains a representative. Now, there's another paradox as well called the new states paradox. I'm not going to give an example of that, but I'll describe what it is. So our last example had 10,000 individuals. Now let's do two examples ago where we had 10,000 individuals in 6 districts. A new states paradox is, what if we added a 7th district with its own representatives? It turns out sometimes if you add a 7th district with its own representatives, 2 of our other districts could have swapped representatives. In other words, one gains, one loses. So it's like, let's talk about an example in America. If Puerto Rico was to become a new state, and they came in, and all of a sudden Michigan lost a representative, but Ohio gained a representative, just because Puerto Rico came in. Does that make sense? So that would be like a new states paradox. 2 states or 2 districts swap representatives because a new state came in, right? Even though we added enough reps for the state. So that's Hamilton's system, named after Alexander Hamilton. Let's go to another system named after another one of the founding fathers. This is called Jefferson's method, named after Thomas Jefferson. So Jefferson's method says these paradoxes that came with Hamilton's method came because we were trying to force ourselves into the standard divisor. And the standard divisor was what was throwing us off. Jefferson's method says, let's use a different divisor other than the standard divisor. Let's just use the correct divisor. I'll talk about what the right divisor is in a second. We're going to divide each population by the right divisor. And instead of getting the quota that we got before, we're gonna get a modified quota using this different divisor. And instead of giving everyone the lower quota and having extra, what's gonna happen is when we give everyone the lower quota, we're gonna have exactly the right number of representatives. So if we want 100 representatives, after we've divided by this correct divisor, we give everyone the lower quota. And all of a sudden, the lower quota gets us to exactly 100 representatives. Does that make sense? And that's what it means to be the right divisor, is that we divided and the lower quotas all add up to the perfect number of representatives that we want. That's what it means to be the right divisor, is that we get the right number of representatives. Okay. So we don't have to ever add any extra based on the decimals. And that turns out to be a method that avoids the Alabama paradox, avoids the population paradox, and avoids the new states paradox. So let's go back to the very, very first one we did. The very, very first one we did with Hamilton's method was these 5 districts. And if you remember, we wanted 100 representatives with these 5 districts. There we go. And so we wanted 100 representatives. The total population was 100,000. And we saw that from last time, our standard divisor was 1,000. Okay with that? So in Hamilton's, we would have had to use 1,000. Had to use the standard divisor. But in Jefferson's, we're going to use a little bit under 1,000. In this case, 975 as what we call the modified divisor. There you go. Now you might ask, where did you come up with the 975? How did we get that 975? And the answer is, I guessed and checked until I got the correct divisor. All right. On a test or homework, what I will say is use a divisor which is 25 units away from your standard divisor. Everybody follow that? So I will tell you, find the standard divisor and go 25 units away from that. With Jefferson, you always go 25 units down. Now, if 975 didn't work and we needed to use 980, then I would have told you use a divisor which is 20 units away from 1,000. So I'll just tell you how many units to go away from the standard divisor. Is that okay? All right. So we're going to use 975. So take 38,343 and divide it by 975. You should get 39.33. I'm going to just round it 2 decimal places. Take 21,230 divided by 975. We get 21.77. 4,899 divided by 975. You get 5.02. 20,405 divided by 975 gets us to 20.93. 15,123 divided by 975 gives you 15.51. Okay. And then Jefferson says, if we found the right divisor, we just lop off the decimals. Notice that the lower quota, 39 plus 21 plus 5 plus 20 plus 15 gives us exactly 100 representatives. Okay. So if we use that 975 as our divisor, then the lower quota gives me exactly the number of representatives I want. Okay. And that's Jefferson's method in the shortest way possible. Okay. That work? All right. So that's Jefferson's method as the method for apportionment. I think I have time for another one. And on this one, I'll kind of show you how this works out. So we're going to have 6 districts. We actually did this one earlier. This is the one where we have 10,078 people, I believe. And we want 100 representatives. Okay. Now, what's going to happen is we're going to have to try different divisors. If you didn't have any hint, what you'd have to do is you'd have to just try a bunch of divisors. You'd have to try maybe 98 and see what that gives you. And then try, if that's too much, try 97. That's too little, maybe try 99. Does that make sense? So you just try a bunch of divisors. And that process of trial and error takes a long time mechanically. Now, the good news is this. If you go to your fair division section, there's a little tab that says Apportionment Excel. Right? Oh. I just downloaded it. And what this brings up is a small Excel sheet. And I'll explain what this does. This calculates the lower quotas for you as long as you type in the populations and the divisor. Okay? So let's type in the population from the table we have. So the population for District A is 2635, for B 712, 2011 for C, 3872 for D, 580 for E, 268 for F. I don't have a District G or District H, so I'm just gonna put zeros on there. Is that all right? Now the standard divisor, we already said, is 100.78. And I'm looking at this lower quotas column right here. This lower quotas column. This lower quotas column tells me that right now, if you use the standard divisor, you're only allocating 97 representatives. That's too few, so we need to start taking that down. So let's take the divisor down to 99. Ooh, that gave me 99. Not quite there yet, but getting closer. Let's go down a little bit further. Let's try 98. Oh, not quite there yet, right? Let's go down a little bit further. Let's go 97. 97 works. Gave me 100 representatives. Notice how quick of a process that was. All right, using technology. So what I'm gonna do, see if I can copy paste these numbers. I don't know yet if I can or not. So what I do is I say, we're gonna use a modified quota of 97. Or did I say modified quota? Modified divisor. That'll give me the modified quotas. Sorry. There you go. I've used 97. Now, I know District A has 27, District C has 7, B has 7, C has 20, D is gonna have 39, E is gonna have 5, F is gonna have 2. Okay. Now, what's gonna happen on the test or on the homework is this. It's gonna use a divisor, which is 3.78 from the standard divisor. Does that make sense? And you'll have to figure out that that means 97, and then fill out the modified quota, and that'll give you a certain number of representatives. Is that okay? Not too crazy? Now, because I am gonna erase this, I want you to think back to the previous version of this with Hamilton's. So just put in your mind 27, 7, 20, 39, 5, 2. If I scroll back up to Hamilton's, I did not get 27, 7, 39, 5, 2, 21, 39, 5, 2. So notice Hamilton's did result in a different allocation of representatives than Jefferson's method. Does that make sense? And that kind of gives you a hint at why Hamilton and Jefferson's methods are different. Right? Hamilton's famously from New York, right? Or was a representative in New York. And Jefferson's representative in Virginia. Whose method do you think would help New York at the time? Gave more representatives to New York. Well, Hamilton's did at the time. Whose method do you think gave more representatives to Virginia at the time? Well, Jefferson's method did. He lived in Virginia. So these were, these were kind of the fights people had. Now, next time what I'll do is I'll cover Jefferson's and method in one more example. And I will talk about the weird thing that can happen with Jefferson's method. Okay? So I'll do that next time. Does that work? And then I'll do there's 2 other apportionment methods. One is called Adams's method, who's famously from Massachusetts. And one's called Webster's method, named after John Adams and Daniel Webster. All right? Does this work? All right. Well, then I will see you all next time. We'll cover those methods. You have all the tools you want to finish the apportionment homework right now, if you'd like. Okay. All right. We'll see you next time.